6 million years ago, in what we now call Arizona, a landscape of unimaginable beauty was just beginning to take shape. The Grand Canyon, one of Earth's most magnificent natural wonders, didn't exist yet. In its place stretched a vastly different world, a terrain that would seem almost alien to our modern eyes. Today, we're embarking on an extraordinary journey through time. Using cutting-edge artificial intelligence and the latest geological research, we'll reconstruct what this region looked like before the Colorado River carved its legendary path through ancient stone. We'll witness a world of flowing waters, lush vegetation, and geological forces that would shape one of the most iconic landscapes on our planet. This is not just a story about rocks and rivers. This is the epic tale of how time itself sculpts the face of our world. To understand what the Grand Canyon region looked like 6 million years ago, we need to transport ourselves to the late Miocene epoch. The world was a different place. The climate was warmer, sea levels were higher, and the Colorado Plateau was undergoing dramatic transformations. Where the Grand Canyon stands today, there was a relatively flat highland. Imagine a broad, elevated plain stretching for hundreds of miles. This wasn't a barren desert like the surrounding areas today. Instead, the region received significantly more rainfall than it does now. Seasonal streams flowed across the landscape, creating networks of shallow channels that would fill during wet periods and dry up during drought. The Colorado River, as we know it today, had not yet established its current course. The river system that would eventually carve the Grand Canyon was still forming, still searching for its path to the sea. Multiple river channels crisscrossed the plateau, some flowing in directions completely different from the modern Colorado River. The rock layers that would later be exposed in the canyon's walls were still buried beneath younger sediments. The ancient Vishnu schist, the Coconino sandstone, the Kaibab limestone, all these geological treasures were hidden, waiting for millions of years of erosion to reveal their secrets. The climate of the Colorado Plateau region 6 million years ago was markedly different from today's arid conditions. The late Miocene was a time of global cooling, but the American Southwest still enjoyed more moisture than the present day. Forests of pine and juniper covered much of the higher elevations. These weren't the sparse woodlands we see today, but denser, more vibrant ecosystems. In the lower areas, grasslands dominated, interspersed with shrublands and scattered groves of deciduous trees. The region experienced distinct seasonal patterns. Summer monsoons brought heavy rainfall, feeding the network of streams and creating temporary lakes in low-lying areas. During these wet periods, the landscape would transform into a patchwork of green valleys and flowing waterways. The sound of running water was constant, a stark contrast to the relative silence of the modern desert. Winter brought cooler temperatures and occasional snow to the higher elevations. The seasonal variation in water flow would prove crucial to the eventual formation of the Grand Canyon. These cycles of abundance and scarcity created the conditions necessary for erosion to begin its slow but relentless work. Volcanic activity was still present in the region, though less intense than in earlier epochs. Occasional eruptions added layers of volcanic ash to the existing sediments, creating distinct geological markers that scientists use today to date the formation of the canyon. The story of the Grand Canyon is fundamentally a story about water. 6 million years ago, the drainage patterns of the Colorado Plateau were in a state of flux. Multiple river systems competed for dominance, their courses shifting with tectonic movements and climatic changes. One theory suggests that an ancient river system, sometimes called the ancestral Colorado River, flowed in a northeastern direction, completely different from today's path. This proto-river drained parts of the plateau but didn't have the power or the route to carve anything resembling the modern Grand Canyon. To the west, another river system drained toward what would eventually become the Gulf of California. These two systems were separated by a subtle divide, a geological barrier that prevented them from connecting. The breakthrough moment, when these systems would eventually merge, was still millions of years in the future. The streams that crossed the plateau 6 million years ago were relatively gentle compared to the powerful Colorado River we know today. They meandered across the landscape, depositing sediment in some areas and slowly eroding others. The process was gradual, almost imperceptible on human timescales, but relentless over geological time. Lakes formed in basins across the region. Some of these were substantial bodies of water, lasting for thousands of years before shifting climate patterns caused them to dry up or drain. These ancient lakes left behind distinctive sediment layers that geologists can identify today, providing crucial clues about the region's past. The groundwater system was also more active than today. Springs bubbled up across the plateau, creating oases of life in otherwise dry areas. These springs supported unique ecosystems and played a role in the chemical weathering of the underlying rock, softening it for future erosion. The Colorado Plateau 6 million years ago teemed with life. The more hospitable climate and abundant water supported diverse ecosystems that would seem remarkably rich compared to the modern desert environment. Large herbivores roamed the grasslands and woodlands. Species related to modern horses, camels, and rhinoceros-like creatures grazed on the abundant vegetation. These weren't the familiar animals we know today, but their ancient relatives, adapted to the specific conditions of the late Miocene. Predators followed the herds. Ancient cats, some with distinctive saber-like canine teeth, stalked the grasslands. Early canids, ancestors of modern wolves and foxes, hunted in packs or alone, depending on their species. The food chain was complex and dynamic, with numerous species filling ecological niches that no longer exist. The skies were filled with birds, many of which would seem familiar to us today. Eagles, hawks, and vultures rode the thermal currents rising from the warming plateau. Waterfowl congregated around the numerous lakes and streams, their calls echoing across the landscape. Reptiles thrived in the warm climate. Lizards, snakes, and turtles were common, taking advantage of the abundant insects and other small prey. The region's rivers and lakes hosted fish and amphibians, though many of these species would later disappear as the climate became more arid. The plant life was diverse and adapted to the seasonal water availability. Grasses dominated the open areas, their deep roots accessing moisture even during dry periods. Trees clustered along waterways and in areas with reliable groundwater. Flowering plants added splashes of color to the landscape, supporting populations of pollinating insects. This ecosystem was in balance, but it was also in transition. The global climate was cooling, and the American Southwest was slowly drying. The abundant life of 6 million years ago represented a peak that would gradually decline as conditions became harsher. Beneath the seemingly stable surface of the Colorado Plateau, powerful geological forces were at work. These forces would ultimately create the conditions necessary for the formation of the Grand Canyon. The Colorado Plateau is a massive block of Earth's crust that has been uplifted over millions of years. This uplift is caused by tectonic forces, the same processes that create mountains and cause earthquakes. 6 million years ago, this uplift was ongoing, gradually raising the plateau higher above sea level. As the land rose, the gradient of rivers crossing it increased. Water flowing downhill gains energy, and that energy translates into erosive power. The steeper the slope, the more powerful the erosion. This fundamental principle would prove crucial to the formation of the Grand Canyon. The Basin and Range province to the west of the plateau was also undergoing dramatic changes. This region was stretching and faulting, creating a series of valleys and mountain ranges. As these valleys deepened, they created a lower base level for rivers draining westward from the plateau. This difference in elevation created a powerful incentive for river systems to connect. Water, always seeking the lowest point, would eventually find ways to breach the barriers separating different drainage systems. When this connection finally occurred, the results would be dramatic. Volcanic activity, while diminishing, still played a role in shaping the landscape. Lava flows occasionally blocked river channels, forcing water to find new paths. These temporary dams would build up sediment behind them, only to catastrophically fail when the pressure became too great. The climate continued its slow shift toward drier conditions. This might seem counterintuitive, but drier conditions can actually accelerate erosion in some circumstances. With less vegetation to hold soil in place and more intense but less frequent rainfall events, the potential for dramatic erosion increases. Between 6 and 5 million years ago, a critical change occurred. The exact details are still debated by geologists, but the evidence points to a dramatic event that would set the stage for the formation of the Grand Canyon. The most widely accepted theory involves the integration of the Colorado River system. Remember those separate river systems we discussed earlier? Around this time, they began to connect. The process wasn't instantaneous. It likely took hundreds of thousands of years. But once it started, it was irreversible. One scenario suggests that a river draining westward from the plateau gradually eroded headward, cutting back into the plateau's edge. This process, called headward erosion, is like a zipper being undone from one end. As the western river cut deeper into the plateau, it eventually captured the drainage of rivers flowing in other directions. When this capture occurred, the combined flow of multiple river systems suddenly had a new, steeper path to the sea. The increased water volume and gradient gave the ancestral Colorado River unprecedented erosive power. This was the moment when the creation of the Grand Canyon became inevitable. Another factor may have been the opening of the Gulf of California. As tectonic forces pulled Baja California away from mainland Mexico, a new drainage route to the ocean opened up. This provided the ultimate base level for the Colorado River system, creating the gradient necessary for rapid downcutting. The combination of increased water flow, steeper gradient, and a newly opened route to the sea created perfect conditions for rapid erosion. The river began to cut downward into the plateau, the first step in creating what would become the Grand Canyon. As the integrated Colorado River began its work, the landscape started its dramatic transformation. The process wasn't uniform or steady. Periods of rapid cutting alternated with periods of relative stability. Flash floods during monsoon seasons did much of the work, carrying enormous amounts of sediment downstream. The river didn't create the canyon alone. The exposed rock walls, once uncovered by the river's downcutting, became subject to weathering and mass wasting. Frost action during cold periods caused rocks to crack and fall. Rainfall carried debris down the canyon walls. Occasional rock slides sent massive amounts of material tumbling into the river below. The river responded to these obstacles by cutting around them or wearing them down. Temporary dams created by rock slides would form lakes that persisted for years or even centuries before the river breached them. When these dams failed, the resulting floods had tremendous erosive power, scouring the canyon deeper and wider. Different rock layers responded differently to erosion. Hard, resistant layers like the Coconino sandstone formed cliffs and steep walls. Softer layers like the Bright Angel shale eroded more easily, creating slopes and terraces. This differential erosion gave the developing canyon its distinctive stepped profile. Side canyons began to form as tributary streams cut their own paths down to the main river. These side canyons added complexity to the landscape, creating the intricate network of gorges that makes the Grand Canyon so visually stunning. Each side canyon had its own story, its own timeline of formation. The rate of downcutting was impressive by geological standards. In favorable conditions, the river could cut downward several inches per century. Over millions of years, this steady erosion added up to thousands of feet of depth. The Grand Canyon was taking shape. As the Colorado River cut deeper into the Colorado Plateau, it did something remarkable. It created a window into Earth's past, revealing rock layers that recorded nearly 2 billion years of geological history. The youngest rocks at the rim of the forming canyon were relatively recent by geological standards, formed during the age of dinosaurs and after. But as the river cut deeper, it exposed progressively older layers. Each layer told a story of a different environment, a different chapter in Earth's history. The Kaibab limestone at the top recorded a time when a shallow sea covered the region. Fossils of marine creatures are preserved in this rock, evidence of an ocean that existed 270 million years ago. Below that, the Coconino sandstone told the story of ancient sand dunes, a desert environment from 275 million years ago. Deeper still, the Redwall limestone contained fossils of coral and other marine life, evidence of yet another ancient sea. The alternating layers of limestone, sandstone, and shale revealed a dynamic history of advancing and retreating oceans, shifting climates, and changing landscapes. As the canyon deepened, it eventually reached rocks so old they predated complex life on Earth. The Vishnu schist at the bottom of the canyon, exposed in the inner gorge, is nearly 2 billion years old. This metamorphic rock was formed deep within Earth's crust, then uplifted and exposed by erosion, only to be buried again by younger sediments, and finally revealed once more by the Colorado River. This geological exposition made the developing Grand Canyon not just a natural wonder but a scientific treasure. Each exposed layer provided clues about Earth's past, helping scientists understand how our planet has changed over billions of years. The Grand Canyon, as we know it today, has been forming for the past 5 to 6 million years, but its appearance has continued to evolve. The canyon we see now is not the final form. It's simply the current state in an ongoing process. Over the past few million years, the canyon has deepened and widened considerably. The Colorado River has cut down through over a mile of rock, exposing those ancient layers we discussed. The canyon's width, in some places exceeding 10 miles from rim to rim, is the result of the erosion of the canyon walls. Climate changes have affected the rate and style of erosion. During ice ages, when glaciers covered much of North America, the Grand Canyon region experienced cooler, wetter conditions. Increased snowmelt and rainfall gave the Colorado River more erosive power, accelerating the canyon's development. Between ice ages, drier conditions prevailed. During these periods, weathering and mass wasting of the canyon walls became more important than river erosion in shaping the canyon. The cycles of wet and dry, cold and warm, each contributed to the canyon's unique character. Volcanic activity continued sporadically in the region. As recently as 1 million years ago, lava flows poured into the canyon, creating temporary dams that backed up the Colorado River into large lakes. The remnants of these lava dams can still be seen today, though the river has long since cut through them. The Grand Canyon has also been shaped by human history, though on a much shorter timescale. Indigenous peoples have lived in and around the canyon for at least 4,000 years, leaving behind artifacts and structures that tell their own stories. European exploration beginning in the 16th century brought the canyon to wider attention. Today, the Grand Canyon continues to evolve. The Colorado River, though diminished by dams and water diversions, still carries sediment and slowly deepens its channel. Rockfalls and erosion continue to widen the canyon. The process that began millions of years ago continues, though at a pace imperceptible in a human lifetime. Standing on the rim of the Grand Canyon today, gazing out at the layered cliffs and the distant river below, it's humbling to contemplate the vast stretches of time represented by this landscape. The canyon is not just a hole in the ground, it's a monument to the power of geological processes acting over millions of years. 6 million years ago, this view didn't exist. In its place was a very different landscape, flatter, greener, more hospitable in some ways. But the seeds of the canyon's creation were already present, waiting for the right combination of factors to come together. The formation of the Grand Canyon teaches us profound lessons about the nature of time and change. Processes that seem impossibly slow on human timescales, a river carrying sand and silt, rocks cracking in the frost, rainfall washing away tiny particles of stone, can create monumental changes when given enough time. It also reminds us that Earth is dynamic, always changing, never static. The landscapes we see around us are temporary, just snapshots in an ongoing story that stretches back billions of years and will continue long after we're gone. The Grand Canyon is still being formed. Every rainstorm, every freeze and thaw cycle, every rockfall contributes to its ongoing evolution. Millions of years from now, if anyone is here to see it, the canyon will look different from how it appears today. Perhaps deeper, certainly wider, with new features and formations we can only imagine. This geological wonder, created by the patient work of water, time, and rock, stands as one of Earth's greatest natural monuments. It's a place where we can literally see deep time, where the abstract concept of millions of years becomes tangible and real. The story of the Grand Canyon is ultimately a story about change, about how small forces acting consistently over vast periods can create something truly magnificent. It's a reminder that the world beneath our feet has a history as rich and complex as any human civilization, written in layers of stone rather than pages of paper. As we continue to study the Grand Canyon using ever more sophisticated tools, from artificial intelligence to advanced dating techniques, we deepen our understanding of this remarkable place. Each discovery adds another piece to the puzzle, helping us reconstruct not just what the canyon looked like 6 million years ago, but how and why it formed. The Grand Canyon remains one of Earth's greatest natural wonders, a place of beauty, scientific importance, and profound inspiration. Its story, stretching across millions of years, reminds us of our place in the vast sweep of geological time and the remarkable processes that shape our planet. This has been our journey through time, reconstructing what the Grand Canyon region looked like before the canyon existed. From a relatively flat plateau with meandering streams to one of the world's most spectacular geological features, the transformation has been nothing short of extraordinary. And the story continues, with each passing moment adding another infinitesimal chapter to this epic tale of Earth's greatest geological wonder.